In this video, I will talk about the definition of equilibrium position for oscillations. It's important to identify equilibrium position at the start of the problem because everything else will be measured with respect to the equilibrium position. So let's first look at the first picture here. There's a horizontal spring and it's doing oscillation on a smooth surface. The original length of the spring is L0, and also with a spring constant K. The mass doing oscillation has mass M. And here is the original length L0. Now, if we pull this object to a new position here, then the object will start doing oscillation along this equilibrium position, which is denoted by this red dashed line. And in this case, is the original length of the spring. Okay, so object is going to do oscillation symmetrically, right, along this equilibrium position. Okay, back and forth. So how do we find this position? The condition for getting this equilibrium position is the net force equals 0 on the object. So F net should be 0. The net force acting on the object should be 0 at such a position. Okay, so it's easiest to find such a position in this situation because it's horizontal. The normal force acting on the object, mass m, due to the ground, is balanced by gravity mg. And if the spring is at original length, there's no spring force acting on it. So that satisfies that net force equals 0. Now let's look at a more complicated situation. If we hang this spring system up, hang it up, like in this picture. Now let's say the whole system is at rest for the first picture. The original length of the spring is L0. Now the object is not going to stay here because of gravitational pull. The spring is going to extend an additional length delta L. Then the system is at equilibrium, meaning that the net force acting on the mass m is 0 again. Okay, so let's find out the condition for net force equals 0. The free body diagram looks like this. It's gravity acting on it, and there's a spring force, F spring. In order for the net force to be 0, we need to have the condition that F spring equals mg. Okay. Now, since we know the spring has an additional stretch of delta L, so K times delta L equals mg. So that gives us the solution delta L equals mg over K. And that can be used to identify the equilibrium position, which is shown again using this red dashed line. Okay, so now if the object is pulled down by an additional amount, and then we'll start doing oscillation, it's going to oscillate symmetrically along this equilibrium position, the red dashed line. Okay, so that's the vertical situation. Now let's look at a more general case. When the spring system is sitting on a slope that makes angle theta with the horizontal. Okay. Now here, because of the gravitational pull again, the spring is going to stretch an additional amount delta L, and then the whole system is at rest. Right now it's at rest. Now according to the condition for determining equilibrium position, let's draw a free body diagram. There's normal force due to the slope. There's a gravity mg. There's also this spring force, F spring. Okay, now the along the slope direction, F spring is going to be equal to mg sine theta, right? Theta is the slope angle. Okay, so that will give us the solution that delta L equals mg sine theta over k. Okay, so that determines this equilibrium position shown by this red dashed line. Okay, and then again, if you pull this m downward, the object is going to oscillate symmetrically along this point, along this dashed line. So now we can see that for the horizontal case, the angle theta is actually 0 degree. So that's a special case here. That means that delta L here equals 0. So that's consistent with our previous result. That gives us this equilibrium position. Now for the 90 degree, we get delta L equals mg over k. So that's also consistent with our previous calculation. Okay, but anyway, it's the general case here that actually contains all the situations that we discussed. So that's the definition of equilibrium position.